Hey everyone. Last time we were talking about really focusing on the kernel of a homomorphism. We talked about various properties, and we left off with discussion of the kernel of a homomorphism. And so just a few kind of quick applications. In particular, we know that the kernel of a homomorphism is a subgroup, right, of the domain of the homomorphism. And so a few examples here. So remember, one of the standard homomorphisms, the important homomorphisms that we had. So phi, I don't know if I gave it a name or not. Oh shoot, I don't know what symbol I used. I'm just going to use phi for now. It was the signum function. If phi from Sn to Z2 is given by phi of sigma equals, and remember it's either 0 or 1. So it's 0 if sigma is even, and it's 1 if sigma is odd. Okay, so then who is the kernel of this homomorphism right here? Well, let's see, the identity in Z2 is 0. So the kernel of phi is going to be the set of all elements of Sn, so all permutations that get sent to the identity. The identity is 0. And so well, that's going to be the set of all elements that get sent to, that's going to be the set of all permutations that are even. And we have a name for that. It's An. Right? So the kernel of phi is equal to the alternating group An. There's another quick proof that An is a subgroup of Sn, right? Because the kernel is always a subgroup. Okay, so next example, we have the determinant. Right? Remember, that is a homomorphism from GLNR to R star, the group of non-zero real numbers under the operation of multiplication. And so who's the kernel of the determinant? Well, let's see. Okay, so the kernel is the set of all elements that get sent to the identity. The identity in R star is the number 1. So that's going to be the set of all matrices, n by n invertible matrices, whose determinant is equal to 1, and we have a symbol for that, SLNR, the special linear group. Right? So here's another quick proof that SLNR is a subgroup of GLNR. So, in fact, one way to show that you got a homomorphism, it's not always the way. Sorry, I just said that funny. One way to identify a certain set as a subgroup is to show that it's the kernel of a certain homomorphism. That is a theme that we'll sometimes consider, or sometimes pursue. One more example. So if phi from Z to Z8 is reduction mod 8, then let's see, who's the kernel? Well, the kernel of phi is going to be the group 8Z, right? It's the set of all multiples of 8. Why is that? The identity in Z8 is 0, so we want all elements that get sent to 0. Well, it's going to be all multiples of 8. Next fact that we'll need, so this is theorem 13.3. So let's let G, H, and K be groups, and let phi from G to H and psi from H to K be homomorphisms. Then psi of phi, which is going to be a homomorphism from G to K, is a homomorphism. So you could paraphrase this: composition of homomorphisms is a homomorphism. And the proof. So let's let A and B be elements of capital G. This proof is just going to be a straightforward computation now. So then what I want to look at is psi of phi of AB. By definition, that is psi of phi of AB. Now use the fact that phi is a homomorphism. So we can split up the inside. And then we use the fact that, that psi is a homomorphism. So this will be psi of phi of A times psi of phi of B. And then we can write this as psi of phi of A times psi of phi of B. And so that completes the proof, right? So that's an easy computation, right? And that tells us that composition of homomorphisms is a homomorphism. Okay, so now got another theorem. This theorem has a name. So it goes like this. So this will be theorem 13.4, and this is called the universal mapping property. Property for cyclic groups. So what this is going to do, and universal mapping properties, these are, we'll see these in other situations. What it's going to do is it's going to tell us how to come up with homomorphisms when the domain is a cyclic group. So let's let G be a cyclic group with generator G, and let H be any group. Now there's going to be two parts to this depending on whether G has infinite order or finite order. So if the order of little g equals infinity, then for each little h in capital H, there is a unique homomorphism phi from G to H such that phi of little g is equal to little h. So what is that saying? It's saying in the case that our domain is an infinite cyclic group, we can have a homomorphism that takes our generator to any chosen element of H, right? So it tells us exactly how to come up with homomorphism, and there's a unique one. So there's exactly one homomorphism that will take our generator to our chosen output. And then for part B, so if the order of little g equals n, then yeah, for each, we have to be a little bit more careful now in the finite case. For each little h in capital H, there is a unique homomorphism phi from G to H such that phi of the generator equals our chosen element little h. Now, this does not always happen, so this is if and only if h raised to the n equals the identity. If you want, put a little capital H there. Right, so the identity in H. Right? So what this says is that we can come up with lots of homomorphisms from our finite cyclic group to H, but it's not quite as easy as in the first case. What we have to do is make sure that our targeted output for little g satisfies this equation right here. So for the proof, okay, so first we're going to prove part A. Right, okay, so let's pick little h in capital H and define. So let me think now, what are we trying to do? So you don't need to write this down, but right, we want a homomorphism from G to H, and we want to make sure that little g gets sent to little h. Well, if it's going to be a homomorphism, then what does g squared need to do? Well, g squared needs to go to g times g, or phi of g times phi of g. That's going to be h times h. So in general, then, we can define phi of g to the n equal to the obvious thing, the only thing that'll work, h to the n. It's automatic. We basically force it to be a homomorphism. So it is easy to check. You should check the details. So it's easy to check that phi is a homomorphism. Now we need to check the uniqueness part. So if, let's say, psi is a homomorphism from G to H such that psi of G equals H, then if we look at psi of G to the n, that's equal to, remember now, we have a property of homomorphisms, that's psi of G raised to the n, and that's true for all possible. I wish I would have said something right here. I wish I would have said right there for all in Z. So please, just to be complete, right? This is telling us how to define the output of the function for all choices of elements in capital G. Sorry. This is equal to, well, let's see. This is equal to h to the n, which we know is exactly equal to psi of G raised to the n, which is psi of G to the n. And so what does that tell us then? That tells us that psi and phi are equal. So therefore, phi equals psi. Right, so we've got a homomorphism, now we've got the uniqueness portion. And now let's look at part B. In the forward direction, if such a homomorphism exists, right? So if we have a homomorphism from from G to H, taking little g to little h, right? So then what do we need to look at? We need to look at h to the n. So h to the n is equal to phi of g raised to the n. Using a property of homomorphisms, this is phi of g to the n g to the n, well, the order of g is equal to n, so this is phi of e, and we know that the identity always gets sent to the identity under homomorphism. Now, in the reverse direction, so let's assume that h to the n is equal to the identity, and so now we're supposed to show that there exists this unique homomorphism. Let's define phi from capital G to capital H phi. So I need to specify what happens to every element in here, and it's the obvious thing. So it's going to be phi of little g raised to, I need to use some other symbol. How about phi of g to the k equals h to the k. Now, we have to be a little bit careful. We just defined a function and I should also be careful here for all k in z. But here's the thing. In a finite cyclic group, g raised to various powers can be equal to each other. So I need to verify that this function actually is well-defined. So let's say to C that phi is well-defined, suppose that g to the k equals g to the m for some integers k and m. Now, back when we were studying cyclic groups, this is, I don't think I wrote down the number of the theorem, but then what that means then is that n divides k minus m, and so k, I'm going to write this, m is equal to k plus n times t for some some t in z. Right? Their difference has to be a multiple of n. So now what do I want to do? I want to make sure that the outputs are the same. So phi of g to the m is equal to h to the m, which is equal to h to the k plus nt, which is equal to h to the k times h to the n raised to the t. We know that this part right here is the identity, so this is h to the k, and that is phi of g to the k, right? So that shows that our function is well defined, right? The same input expressed differently, right, by different different exponents gives us the same output, right? So it's well defined. The fact that it's a homomorphism is really automatic. And the uniqueness is exactly, the proof of uniqueness is just the same as in part A. So let's just say check that phi is a homomorphism. I mean, we basically just forced it to be so by our definition, right? We said phi of g to the n is or I guess I use a different symbol, phi of g to the k is equal to h to the k. We're telling this function to be a homomorphism. The proof of uniqueness is the same as in part A. So that completes the proof of what's called the universal mapping property. So let's think about what this theorem is actually saying. All right, so we have a cyclic group. All right, there's our capital G. And we want a homomorphism to H. Now, a cyclic group, and what does it mean to be a cyclic group? It means that every element in the group can be built as a power of little g. Right? So everybody in the group is of the form g to the, well, let's use k, g to the k. Now, we've chosen a particular element over here, little h, and we say, well, we want g to the 1. We want g to go to little h. Well, if it's going to be a homomorphism, then you have absolutely no choice but to send it to h to the k. Now, in the finite case, of course, you've got to make sure that this actually would be well defined. That's where this equation h to the n equals the identity comes in. But this is the only thing that would work to make it be a homomorphism. And so I want you to now think about linear algebra. Right? There's an analogy with linear algebra. Just as the generator is the building block of a cyclic group, a basis is the building block of the set of building blocks for vectors. Right? Every vector can be expressed as a linear combination of your basis vectors. And now think about what would happen in linear algebra. If you want to define a linear transformation, what do? You specify where you want the basis elements to go, and that will determine a unique linear transformation. You just say, okay, I want my basis vector number 1 to go here, my basis vector number 2 to go here, and so on. And that tells you how everybody else has to get sent under the linear transformation. That's exactly what's going on right here when it comes to the universal mapping property. Specify where you want your generator to go. You want it to go to this element little h, and everything else has to follow along, right? So by specifying where the generator goes, it tells you where everybody else in your group goes. And I think I'm going to stop here, and then we're going to pick up, we have a bunch of applications to the universal mapping property, but I want to do those as in a sort of self-contained chunk. So we'll stop here, and we will see you next time.